this set of videos, we're going to start thinking about higher order differential equations, and we're going to do that by discussing linear ODEs of the nth, n goes down below, nth order. And this type of differential equation takes the form as follows. So if we wanted to write down an initial value problem for this type of differential equation, it would look like having some function a sub n of x multiplied by an nth order derivative, and for every derivative we have, we would multiply by some function a like that until we start to get down to the lower order derivatives that we're used to, a1 times the first derivative dy dx, and maybe some a0 multiplied by just y, and all of that can be equal to some g of x. And then we have initial conditions for an initial value problem. Your y of x0 equals y0, but then different from what we've had before, we specify additional conditions. Y prime of x0 equals y1, so on and so forth, up until we get to the n minus 1th derivative of x0 equal to some y sub n minus 1. And so what's important to know here is that when we have these nth order initial value problems, we need to have n initial conditions. So instead of stopping after only that first one like we normally did, I added a bunch more, went up to the n minus 1th derivative, just one short of the highest derivative. Since we start from no derivatives at all, when we add those all up, we would get n. The reason we need this is because we're going to have many more unknown constants in this type of problem. So having that many initial conditions lets us solve for all of the unknown constants. In the general solution. And then, just like when we learned about first order differential equations, we're going to go ahead and have an existence and uniqueness theorem. That's given with sort of the same conditions we had before, just now we have more functions to think about. So if all of these functions that multiply by y and its derivatives here are continuous, and g of x is continuous, so that function on the right hand side of the equation, and a sub n of x not equal to 0 over some interval, then for any initial condition, initial x value, x0, the initial value problem has a unique solution. So this is going to be the same way that we checked existence and uniqueness for first order equations. We have all these functions and we check if they're continuous. So do we divide by 0? Do we take roots of negative numbers? This verifying that an is not 0 is actually checking that not equal 0 condition. Just imagine you could rearrange this, divide everything by an, and then an equals 0 causes problems for you. And then we figure out the interval where that happens. We define all the like bad values we want to avoid. And then we find the interval that contains our initial condition x0. And whatever interval that gives us, that's where we know the initial value problem has a unique solution. Just because there are more functions to check, it'll just take a little bit longer. We're doing okay on time. So something kind of related to this are boundary value problems. So now that we have multiple conditions in an initial value problem, we actually have the opportunity to specify those conditions in what's known as a boundary value problem. So for two values a and b, and x between them, we think about the second order differential equation, a2 second derivative y plus a1 first derivative y plus a0 times y equal the sum g of x. And in our initial value problem, we would specify like y of x0 equals y0, sorry, y of x1 equals y prime of x0 equals y1, so on and so forth. But now instead of specifying many initial conditions, we're going to specify two boundary conditions. So we're going to say at this value a, the first possible x, I'm going to specify that y has to be y0. And instead of doing like y prime a equals y1, which is how an initial value problem is set up, I'm going to go ahead and say that y, when I look at the last possible value of x, b, that's going to have to take on some value y1. It would also be possible to specify derivatives. On this boundary. So I could have done y prime a equals y0, y prime b equals y1. That would also be fine. I still end up with two conditions. The reason why I wanted to bring this up right after that existence and uniqueness theorem is because boundary value problems don't meet the same conditions as initial value problems for that theorem. So you can have existence and uniqueness for an IVP, for an initial value problem, but that does not guarantee, so emphasis does not guarantee existence and uniqueness for a boundary value problem. Sorry, I try to write those capital letters for you. I should be consistent. And in the next video, we'll go ahead and look at some examples that make that clear.